Hello everyone. The topic for this video is the Clausius-Clapeyron equation. So before we dive into this equation, just as a quick refresher, we're going to talk about the vapor pressure and the heat of vaporization. So remember that the pressure exerted by a vapor when it's in dynamic equilibrium with its liquid is what we call the vapor pressure. And this vapor pressure is going to increase with increasing temperature. Okay, and let's also remember that heat of vaporization is going to be the amount of heat energy required to vaporize exactly 1 mole of the liquid. Okay, and we're going to use that heat of vaporization in the Clausius-Clapeyron equation. And boiling point, just remember that the normal boiling point of a liquid is when it's at exactly 1 atmosphere. Okay. So as we increase the temperature, we're going to see an increase in the vapor pressure. And keep in mind that small changes in temperature can make big changes in your vapor pressure. So if we look at water for a second at about 80 degrees Celsius, and I'll change the color so we can see the dots that I'm making. But right here at about 80 degrees Celsius of water, and we compare that to a change of 20 degrees Celsius up to 100, so going from 80 to 100 degrees Celsius, that 20-degree change can make a big difference in the pressure because we see that it's less than 50 kilopascals beforehand, and it's more than doubled from that 20-degree Celsius change. And keep in mind that we said the normal boiling point is at 1 atmosphere, but that is equal to about 101 kilopascals. So this this horizontal line right here, that is representing the normal boiling point. Okay. Also, keep in mind that when you're looking at these curves, that they look almost like an exponential function. And so that's going to be important because when we look at the Clausius-Clapeyron equation, we're going to see that we take the natural log of the pressures. And if we take the natural log of the pressure and compare that to the inverse temperature, which is 1 over T, we're going to get a linear equation. Okay, and this is great because then we know from the slope of the line that that's going to be equal to our heat of vaporization divided by our gas constant. And our gas constant is always the same for ideal gases. Now, notice that for that R value, we're using the 8.314. And we do that because enthalpy of vaporization values, those are going to be in kilojoules. Okay, so we need the gas constant that has units of joules in them. Now, also remember that most of our heat of vaporization values, those were going to be in kilojoules per mole. So if we're wanting the units to cancel out with that gas constant, one of the first things you're going to want to do is convert that heat of vaporization value into joules per mole. Okay. Now, the Clausius-Clapeyron equation is listed down here in the bottom left-hand corner. We're going to take the natural log of the ratio of two pressures. And remember that P1 and T1, those represent your initial conditions, so your initial pressure and initial temperature. And then the subscripted 2's, those represent your final conditions. So this is the same thing that we saw in gas laws, where you may have had P1 V1 equals P2 V2. So anyways, this is the natural log of your two pressures, the ratio of the two of them, equals the negative heat of vaporization divided by your gas constant, and then times your inverse temperatures, and it's always final minus initial, so that's why the T2 starts out. Okay, also keep in mind that those temperature values, right, T must always be in Kelvin. So that's going to be another thing that we have to do, is constantly convert the degrees Celsius into Kelvin or vice versa. And keeping in mind that a temperature in Kelvin, that's going to be equal to your degrees Celsius plus 273.15. Okay, so we're either adding or subtracting that 273 value. Okay, so based on that Clausius-Clapeyron equation, we can solve for one of three things, right? We can either solve for the heat of vaporization, or we can solve for a pressure or a temperature, but we have to be given all of the other values. And I think it's easiest if you always set it up where you're solving for either P2 or T2. Okay, so you'll be given an initial set of conditions and then asked to solve for one of those three variables. So in this first example, they are giving us a temperature. So we want to go ahead and assume that that temperature is going to be our T1 value. Okay, so at 57.8 degrees Celsius, the vapor pressure of carbon tetrachloride is 54.0 kilopascals. And I didn't mention this in the last slide, but the pressures can be any unit. Temperature we know has to be in Kelvin. Pressure can be in any unit as long as they are the same. So if we're starting out with kilopascals, we have to end with kilopascals. If they gave us two different pressures of two different units, we would have to convert one to match the other. But they give us a vapor pressure, and they're saying it is at that temperature. So we're going to go ahead and label this as our P1. And they give us the delta H value, the enthalpy of vaporization is 33.05. Use this information to estimate the normal boiling point for carbon tetrachloride. Okay, so if they're asking for the normal boiling point, they must be asking for the temperature. So they're asking, what is T2? And the reason that we know that is because we know that based on the definition of the normal boiling point, that has to be at 1 atm. Okay, so that's going to be our P2. And so we can already tell we're going to have to change those pressure units so that they match. And it may be easiest to keep that 1 atmosphere and actually convert the kilopascals into atmospheres. Or you could do it either way. So actually we know that 1 atmosphere is equal to 101.325 kilopascals. So since we know that, let's go ahead and just say instead of saying at 1 atmosphere, we're going to be at 101.325 kilopascals, and that is the normal boiling point pressure. Okay. Now, another thing that we have to do is convert that temperature into Kelvin. So it's good to go ahead and take T1, which is equal to 57.8 degrees Celsius, and let's go ahead and add that 273.15. Okay, so T1 should be 330.95. And based on significant figures, remember when you're adding numbers together, it's based off of the shortest number of decimal places. And your given value goes out to the tenths place, which means that based on significance, it goes out to the tenths place in your answer as well. But we're keeping that 5 because we want to prevent round-off errors. So T1 is 330.95 Kelvin. Now, another thing that we want to go ahead and convert is that enthalpy of vaporization. So notice how the first thing I'm doing is I'm just getting everything in the units that I need. I need the pressure units to match up, I need temperature to be in Kelvin, and I need that delta H value to be in joules per mole instead of kilojoules per mole. Okay, so we know that it's 33.05 kilojoules per mole. And because of the prefix kilo, we know that there are 1,000 joules in 1 kilojoule. Okay, so our enthalpy of vaporization value should be 3.305 times 10 raised to the 4th power. And that is in joules per mole. Okay, and I'll go ahead and switch my color back to black here. We are done with converting all of the units. And now we can finally set up that Clausius-Clapeyron equation. So remember that the Clausius-Clapeyron is the natural log of your P2 over P1. So final minus initial equals the negative delta H value over your gas constant R times 1 over your final temperature minus the inverse of your initial temperature. Okay, so we're going to start plugging in some of those values. It might be easier to chunk this up and take it one piece at a time and go ahead and calculate what those numbers are. So the natural log of P2 over P1, we know that the final pressure, P2 is supposed to be at normal boiling point, so that's our 101.325. We know that that's in kilopascals over the initial pressure of 54.0 kilopascals. Okay, so the units will cancel, and we're going to take the natural log of a unitless number, and we can go ahead and solve that piece and find that we get 0.62935. Okay, I kept 4 digits, which may be too much, because the 54.0, that is 3 significant figures. And so with those 3 significant figures, that means that we need 3 decimal places in our answer. So technically I only needed to have that as, let's rewrite this, 0.6294. Okay. Not that it matters if you keep too many digits, but just to keep this simple, if I have 3 sig figs in my calculation for logs or natural logs, then my answer should be the same number of decimal places as the smallest number of significant figures. So you may have to refresh your sig fig rules with natural logs. So that's the answer to the first part. Then the second piece, I can go ahead and solve for that as well. We've got our negative delta H vaporization, and you're welcome to plug this all in at once. I just find it easier if you do it one piece at a time. So the enthalpy of vaporization value they give us, and we've already converted it to joules per mole. So that is negative 3.305 times 10 to the 4th joules per mole divided by the R constant, which never changes. That's the 8.314 joules per mole Kelvin. So our joules and our moles will cancel, and we've got 1 divided by 1 divided by Kelvin. So that kind of flips that Kelvin up to the top. So we'll get units of Kelvin once we solve this. Okay, and so if I solve this out, both of those numbers have 4 significant figures. So I want 4 sig figs in my answer and keep an extra digit just to prevent round off errors. And so I'm going to get negative 3.975, and 1 extra digit would be a 2. Remember, I'm subscripting any numbers that aren't significant, and that is times 10 raised to the 3rd power and Kelvin. Okay, so now I'm going to rewrite this on the next page, and I'm just going to keep the two numbers that I have here that I've calculated so far and plug those into this original equation that I started with. All right, so we have that 0.6294 equals negative 3.9752 times 10 to the third Kelvin. And we're going to have to multiply that times 1 over the final temperature, which we don't know. That's what we're trying to find, minus 1 divided by the initial temperature. And remember, the initial temperature in Kelvin was 330.95. Okay, so at this point, I would find it easiest to probably go ahead and distribute. You could go ahead and solve for this piece, the 1 divided by 330, or you can go ahead and distribute and solve by multiplying the negative 3.975 times the 1 over T2 and times the 1 over 330. So that's what we're going to do. That gives us 0.6294 equals, and maybe I can ignore that piece for now and throw it back in later, but we've got negative 3.9752 times 10 to the third Kelvin, and now that's divided by T2, so all I'm doing is basically multiplying by the 1 on top, and then plus, and it's plus because I've got a negative sign here, right, and a negative sign here. So those are going to cancel out to be plus negative 3.975 times 10 to the third Kelvin divided by 330.95 Kelvin. All right, so my kelvins cancel out there, and as you can see, I'm only going to have a Kelvin unit left, and so my temperature will be in Kelvin. So if you want to, you can ignore the units as long as you keep up with all the units canceling and knowing that at the end of the day, your final temperature is going to be in Kelvin. Okay, so next we're going to probably divide these two numbers out and get it out to one solid number. So it's going to be equal to, we'll just put quotes here, it's going to be this first piece plus, should be 12.011, 4 significant figures, plus keep an extra because we've got 4 sig figs that we're using. Okay, so now I should be able to subtract the 12.01 from both sides of the equation. Okay, and when I subtract those two values, remember it's all about the shortest decimal place, right? So my answer should go out to the hundredths place, and I can keep one extra digit of significance. So that becomes negative 11.38, and then 2 to keep an extra digit. And so that has to be equal to everything in the quotations that I've been ignoring. That's the negative 3.975, 2 times 10 to the third Kelvin divided by T2. Okay, so it's getting pretty simple now. We see that we've got two negative numbers, so we could go ahead and cancel those out, make those positive. So we can ignore those. And T2 should be equal to, remember if we bring the T up here and then force that 11.38 underneath, we get 3.9752 times 10 to the third Kelvin divided by 11.382. Okay, so at the end of the day, you should get 300, and I'll write it down here, 349.3. And in terms of significant figures, it looks like we've still got 4 sig figs for all of these, so we've still got 4 sig figs in our answer, and that is in Kelvin. Now, typically they're going to want it in degrees Celsius, so of course to convert it back to degrees Celsius, we have to subtract that 273.15. The shortest decimal place is the tenths place, so our final answer should be the tenths place, and that gives us 76.1 degrees Celsius. So we actually end up with 3 sig figs at the end because of that subtraction step. Okay, so we're going to do one more. In this example, we're doing the opposite, right? We're given 2 temperature values, and we're asked to solve for the pressure. So this time, the temperature of boiling water at an unknown elevation is 83.0 degrees Celsius. What is the atmospheric pressure in torr at this elevation? Okay, and we're also given the enthalpy of vaporization is 40.7. So because we're dealing with water, we have to create our second set of conditions, or our initial conditions in this case, right? Because if this is the unknown elevation and what is the pressure at this elevation, then these must be what we're solving for, right? So this pressure must be P2, and that forces this to be T2. So we need to know what the initial conditions were. And because we're dealing with water, we know that the normal boiling point of water, right, is 100 degrees Celsius. And remember that all normal boiling points are going to be at 1 atmosphere. All right, so personally, I think it's easiest if we keep this in atmosphere until the very end, and then we can just switch it back to torr, and that way it just keeps the math simple because we're dividing by 1. So this is going to be our T1 and our P1. Okay, so of course we need to make sure we convert all those units. Pressure we're going to leave alone, keep that in atmosphere for now. And temperature needs to be in Kelvin, right? So our T1 is going to be equal to 273 plus 100, so that's 373.15 Kelvin. And T2 is going to be that 273 plus 83. Out to the tenths place. So in Kelvin, that should be, let's see, I should have that. Oh, here we go. Sorry, it's 356.15. Okay, we also need to deal with that enthalpy of vaporization value. Of course, we need to convert it to joules. And remember before that we multiplied by 1,000, which is 10 to the third. So you might find it easier with these enthalpy of vaporization values if we have something like 40.7 kilojoules per mole, and we know we need to multiply that by 10 to the third. Then I can just simply say that that's equal to 40.7 times 10 to the third joules per mole. It's not scientific notation, it's not proper scientific notation, but it works because this is not the answer we're reporting, just the answer that we'll use in the calculator. So I think we've converted everything that we need to. We've got our pressures in the units that we want, temperature, and enthalpy of vaporization. So starting out with the Clausius Clapeyron, we've got the natural log of P2, which is what we're looking for, divided by P1, which is conveniently equal to 1, right? So we can almost go ahead and ignore that as long as we know that P2 is going to be in atmospheres when we're done with this. So if we can keep that in mind, we can ignore that 1 and see that we just have the natural log of P2. Now that's going to be equal to your negative enthalpy of vaporization value. Remember, it's times 10 to the third. Okay, and that's going to be in joules per mole divided by your R value, 8.314 joules per mole Kelvin. So again, depending on how particular you want to be, you can ignore the units as long as you make sure that they are matching up. Joules and moles cancel out, which will leave us with Kelvin. So the natural log of P2 is equal to, and we divide those numbers out, we should get negative 4895. And we've got 3 sig figs in our enthalpy of vaporization value, so that 5 is just an extra digit that we're keeping, and our units are Kelvin. Okay, and then we're going to multiply that by the inverse temperatures, 1 over T2, which is 356.15 minus the 1 over 373.15. Okay, we can plug that into the calculator, get back a single value, which should be 1.279. And trust me that 4 sig figs is plenty on that. We're going to be limited by the 3 sig figs here anyways, and trust me, it's at least 4 sig figs in your answer there. So that's going to be times 10 to the negative 4th. And this is in Kelvin inverse, right? Because we have Kelvin on the bottom here for each of these, and negative 489.5 Kelvin. So those Kelvins will cancel out, right? One on top and one on bottom. And so overall, when we multiply the two numbers together, we should get the natural log of the final pressure is equal to negative 0.626, and we'll keep one extra digit until we're done. Okay. Now, if we want to take the opposite of a natural log, remember that's going to be your exponential function, which is your little e. So if we raise everything to the e, we can get the e and the natural log to cancel out. Remember, this is not the double E key that you use for scientific notation. This should be a lowercase e in your calculator. So P2 is going to be equal to the exponential function raised to negative 0.6262, and that should come out to be roughly 0.5346. Okay, and again, based on the number of significant figures here, we should have the same number of decimal places in our answer, which we do. Thankfully, those both match at 3. Now, remember that the pressure, we said that the pressure was going to be in atmospheres. So if they're asking for it in torr, our last step is to convert to torr, and there are 760 torr for every 1 atmosphere. And so our final answer, rounded to 3 sig figs, should be about 406 torr. Okay, and the last thing before we finish up with this topic is just always make sure to check your gut based on what you think is supposed to happen. So if we go back to these graphs, remember, as temperature increases, pressure should increase as well. Okay, so if I look here at this first example, we've got T1 and T2 and P1 and P2. So remember, as we went from P1 to P2, we went from 54 up to 101. We're increasing in pressure, and so we should see the temperature increase. And we found that T2 was equal to 76 degrees Celsius, and we started out at 57 degrees Celsius. So as the pressure went up, so did the temperature. And then in our second example here, this time we've got both of the temperatures. The initial temperature was 100 degrees Celsius, and we dropped down to 83 degrees Celsius. So we should hopefully see a drop in the pressure. And remember, 1 atm is 760, so we went from 760 torr down to 406 torr. Okay, so make sure that if the temperature goes up, pressure goes up as well, or vice versa. If temperature goes down, pressure goes down. Okay, so this ends our topic on the Clausius-Clapeyron equation.